All right, today we'll be talking about something that's a little bit outside my wheelhouse, to be honest, but I'll try to do my best to make sure that everything is accurate and coherent. I know it's been a while since the last discussion, but I've been very busy, and hope, hopefully in the future there is more. I have a lot of interesting ideas, but we'll have to see what happens. Anyway, today we'll be talking about the natural gradient descent, or really more specifically, sort of going over this quantum Fisher information and an example implementation in TensorFlow-Quantum. So first, we'll be going over classical Fisher information, then quantum, then some implementation. And just before I get off or do anything, I want to say that most of the math in this sort of thing comes from a 2021 quantum paper, Fisher information in noisy intermediate scale quantum applications. It's a great review. I highly recommend it, and it'll be linked below. If there's other sources, I'll be sure to mention them as they come up. So on this note, we first need to get into what the classical Fisher information is. And so this has a sort of rich history in classical machine learning, and it is somewhat well known. Basically, it's the information matrix for the KL divergence. So the KL divergence is simply a way to measure the divergence between two probability distributions. It's also called relative entropy. Basically, it's a non-symmetric function. So basically, if you have two probability distributions, P and Q, KL divergence of P comma Q is not necessarily equal to KL divergence of Q comma P. Note that KL, if you were wondering, stands for Kullback-Leibler. I might be messing up that pronunciation. So this divergence specific is not the setting we want. This divergence is the sum over these parametrized, in this case, probability distributions, defined by the following equation. You can immediately see how this is not symmetric, because clearly P and Q do not contribute equally to this equation, or equivalently to this equation. So if we want to get this information matrix, we can sort of consider that specifically in this case, we're measuring some sort of distance between probability distributions. So we have some, where this is some vector, right, of parameters. So this isn't just a single parameter. I can't really do typeface bold and when I'm writing like this, though. And so when we have this, we can say that Q of theta is just equal to P of theta plus some little noise, or plus whatever the difference is. So we have some vector here, and this is just whatever the difference is. So this could be all zeros, which would just make it equal, or it could be 1 and then it could be everywhere else. But it's just some vector that represents the change in parameters around theta. So to get this metric, or to get this information matrix, we want to take the second derivative, right? Because this is going to be a square matrix with the size of, depending on the size of the parameter space. So we have the partial derivative with respect to some specific example, delta I these are, yeah, in case I wasn't clear, actually, that these are supposed to be actually lowercase deltas, not sigmas, which is what they might look like. So we have this partial derivative with respect to this summation here, p of theta log p of theta over p of theta plus delta. And once again, these are vectors here. Maybe I should designate them some way. I'll put a little arrow above them. That's probably for the best. So if we want to do this out, it might be helpful to rewrite this equation. And once again, just to emphasize this point, a lot of this comes from the previously mentioned paper. So I want to give credit where credit is due. This is not an original derivation or anything like that. And so we have this is equal to, if we write it out, we have this log p, oh, that's not, log p of theta plus this parameter here, sigma or delta. So we can then realize that this is effectively equivalent to the expected value, right? Because the expected value is the probability times the actual event. And since this is the probability here, we can write it in the expected value. I'm just going to skip these steps for clarity's sake. It's not really important that we go through this entire derivation, that I'm realizing that now. But basically, we can realize that this term is right here, is equivalent to you can do this whole chain rule and product rule out, and you'll get a long expression that can be combined with these earlier expressions to yield. Once again, we're just skipping steps here because we don't need to go through all of this algebra to effectively get the known result. So up here we have this sort of original formulation, which is this whole equation. And then we can also say that this is equivalent to 1 over p of theta partial p of theta over theta j p of theta theta I. And so in this case, this may look more like the Fisher information. I can say this is equal to F. Now the classical Fisher information, which probably aligns with what you've seen before. This isn't meant, if you've never seen Fisher information before, this is all going to be too much, but this aligns. You might have seen the following expression before for Fisher information. That is the expected value of gradient log p of theta times the gradient log p of theta transpose. So if we consider the expected value, this is at each position of theta. This is the equivalent to the probability distribution, or p of theta times this. So we can get the usual sort of, if we remember that the gradient of log of p of theta is equal to the gradient of p of theta over p of theta because the log just gets differentiated through. Because if you remember, and once again, this is a natural log, the derivative of natural log of x is 1 over x for anyone who doesn't remember calculus. And so if we have this formula, right, I mean, this is dependent on a specific j, but in this case, if this is some I, and this is some with respect to some specific I, and this is with respect to some specific j, or this is partial with respect to some specific example, where we have, these can also be swapped in this case. This is with respect to, I'm just writing out shorthand. Then we have p squared over here, so we have 1 over p theta squared, right? Because these are multiplied. That isn't part of the differential theta, or sorry, partial of, and here I'm going to write it out with respect to theta I, p of theta. Remember, because this is the gradient, so if we're looking at a specific example, it's the partial derivative. And we can swap these, right? They're just being multiplied. So I can write theta j here. It's not a big deal. P of theta over p over with respect to I. And so this is what this comes out to be, right? If we do this operation, but then remember we have the expected value. So if we do this whole thing, this is going to be a sum over all the possible combinations, and it's going to be p of theta times this, which is clearly going to cancel out one of these. And so we're going to be left with 1 over p. The sum still over here. I'll write this sum of 1 over p of theta. The partial, I'm going to shorthand it now. See, I can just write partial j, partial I, p of theta. And this is equivalent, right? This is exactly what we just derived right here. So you can see how these forms are equivalent depending on what background you come from and what you've seen. So now with the established Fisher information, classical Fisher information, and note that I'm not really talking about this as an important optimization concept. You can think of it sort of as the, like from the optimization standpoint, as sort of the amount of information that some variable carries about the distribution, or in this case, the model output. And that's why it's called the Fisher information matrix, is because it's this information that sort of is the concept here that this is conveying inside this matrix. It's a really common, it's in a lot of fields. I'm not gonna talk too much about it, both because you probably know about it and because I don't know that much about it. But moving over to the quantum version of it, if we consider that, remember with the KL divergence, we were measuring the difference between probability distributions. We can do that in a quantum sense as well, right? We trivially have a way to measure the similarity between, oh wow, why did I don't know why I wrote it like that, between two quantum states already. This is, everyone's got this in quantum, right? We have our fidelity. So this right here is the expression for fidelity, this square of the inner product. So if we have this for fidelity, it's pretty trivial to get distance. We can see that the distance between some theta is here, and once again, I'm writing this in this sort of delta added on. The distance between these two states is 1 minus the fidelity of them. All right, that's straightforward enough. So here we have the classical distance. Here we have the quantum distance. Now right here, we just went through the process to get this information matrix. So let's do the exact same thing. I really should have written plus delta here. Let's take the partial derivatives with respect to this. However, first we're going to we're going to use a handy trick. We know that since this is this is just true, we have this, right? This is some state, we have parameters plus whatever the change is, we have the original state plus a sum over all of these changes and the partial with respect to that. And that's trivially true for any sort of discrete sort of system, right? This is readily apparent for these small sort of displacement factors. And this is just a handy way to write it out. So if we have this nice little format, right, this sort of makes sense, right? We have some thing that we're changing, right? This is a specific change. This is how much it changes with respect to that variable. And since we're just have the change and how much it changes or how that change influences things, combine them, we just get this back. That's sort of what derivatives are basically doing. So we have now another way to think about this would be to think about this in a continuous, right? We have some x, and then this is dx, right? This is the partial, and so we just have the total of whatever the change x is impacting on this phi. But that's not, that's just another way to conceptualize it. So we can rewrite this fidelity operation as here as now we have this expression that we're just putting in. All right, we can expand this out to be 1, because if you notice this, the inner product of something with itself is always 1, and then we have this sum, once again, where we just have, now we just have this inner product here with the partial, so now this is our fidelity operation. So our distance in total would be this expression. So now we can simply expand this out. And so if we square this, right, we have 1 minus 1 plus, we have, in this case, the we have here, we have this term. And because it is the absolute value here, now before we add the next term, it's worth remembering that this is in this complex world, right? These wave functions live in the complex plane, that the absolute value is, in fact, the object times its conjugate transpose. So we have, in this case, 1 plus the sum, right, of this partial, but then we have it times the complex conjugate. So 1, obviously, complex conjugate. This is fine, because we're assuming the parameters are, in this case, real numbers. But now we have this. This is a operation that is not in its complex conjugate form, but is trivial to do. We can simply, and it might be good to actually make this a different variable, even though it's iterating over the same scope, it's just referring to a different object. Where now, right, if we want the complex conjugate of this is equal to this, that's what, you know, bracket notation is used for. That's the whole power of why we're using these things. So this is trivial to do, right? Now we have the partial of j so now we have this formula. So now we can say, okay, now we can add it to, right? So if we did this 1 times 1, we did this function times 1, now we're doing 1 times this one, we have over here this whole thing written out. And now we have that times that, so we have plus sum of I this time, keeping track of these, that's a j, keeping track of these variables as best as possible, the partial I. And now we're going to have this multiplied by this j. All right. So let's see what we can do to simplify this. Oh, I should put another parentheses here. So first we can distribute this negative sign pretty easily. So this 1 and 1 cancels out. So we have or we can simplify inside first. It doesn't really matter. So if we want to add these two, it's pretty straightforward. We know I and j are iterating over the same set, so we can simply do we can just add them, right? And so if we're adding them, but it's over the same operations, we can just add these terms, right? These can just be added together. So we can say that this is over I, and we're factoring out this delta. And so we have this term here, the partial of I, and then we add it to this term here. And once again, this is partial with I because we're summing over the same exact things. And these all the points line up, right? It's not, we'll see later that if they don't line up, it's different. But in this case, each j is the exact same as each I when you're adding them together. So we can combine them and we see that we get this output. So now let's add it to this thing over here, which is the combination of them. So if we're multiplying together, we can simply do this now. We can write this as two sums, or we can write this as just ij. Either way is fine. I'm just going to write ij for compression. This is the same as summation multiplication. You can look up like double series, I believe is what it's called. And this is just a property of sums, right? That you can multiply them or you can write them as double sums, which makes sense if you expand the sums out, right? You're multiplying them, you're multiplying each pair. But we don't need to get into calculus right here. So we have some delta I, delta j, combine this with what we actually have here, which is a multiplication. So we have this partial with respect to I'm just trying to make my notation consistent. You can have I or j, right, when we're multiplying them, because multiplication is, you can swap the order and it doesn't change the output. You can rewrite this as I and j. So here I'm just going to swap these indexes for consistency with the original paper. So we have this term, right? Where here, this is this term. Oh, sorry, this is this term, right? This is the partial on the first, on the left-hand side of the inner product, but we swap j with I here because we're multiplying them, so you can swap them either way. It's the same. And then we have this right here with the partial with respect to j. And then this, so this is going to be almost our complete summation. However, we have to remember that when we canceled this out earlier, we put a negative here. So we also, oh, that was almost bad. So we also need to put a negative right here. All right, now with all of that work done, and that is taking way longer than I thought it would, we can now begin to differentiate it. So if we look at this term, and we do the same derivative, right, that we did before, we have this terminology. Then we can simply take the derivative with respect to delta I and delta j, and we can see that this term right here will, and even if we swap the I and j, whichever one comes first, in the derivative, we can see that this will equal 0. And so this right here becomes 0, right, if we take this derivative, because when we take the derivative with respect to one of them, whichever I or j we can write this as, this becomes just the term, and then we take it again with respect to the other delta, but there's no deltas in there, right? So if we have this equation, let's just suppose it's delta I times x, right? And we take the second derivative, even just with respect to delta I. After the first derivative, you just get x, but then the derivative of constant is 0. However, that's going to come back. We'll mention that in a little bit. It's not truly 0. But for now, we can pretend it's 0. So now we just need to take the derivative with respect to the second term, which is trivial, right? The first derivative eliminates this term. The second derivative eliminates this term. So it's pretty readily apparent that this derivative is just going to be this right here. That whole thing right here is going to be the derivative, because these terms just go to 1 as each partial is differentiated. However, there's one more thing that we have to take into consideration, and that's the fact that when we wrote out this handy equation earlier, right here, this has to be a pure state. So we have to have that the fidelity of this, or we have to have that this inner product of delta plus theta, delta plus theta squared, this has to equal 1 because this is a pure state. So with that, if we write this out again in the format of this earlier equation, we can see that this equals this. So here, right, we have this parameter plus, it's not very nice, plus this partial, that's an I. And so this is our full sort of equation, right? So if we do the inner product of these two, we clearly have this state in both cases, right? So this times this, but remember it's the complex conjugate. We have this and this. Okay, so now we have this and this, and then this and this, right? Because we're just doing FOIL, sort of basic expansion techniques. So we'll get the exact same thing that we did before, just right here, right? We just have the exact same terminology. So we have this sum over I delta. I keep saying I or J and writing the other one. And then we have this multiplication by this sum here. So we have this, and then we have the partial I, and then the wave function. And then we add it to this partial I of the wave function times the wave function. And this is sort of our complete, right, expansion again. And so this is, if we're writing this out, slightly different here, because if we look at the expansion previously, you notice this term is different from this term. And the reasoning for that is the fact that when we have this expansion, right, there's not this constant over here. That's the, here, if we go over here, we're not doing this. The origin of this term is the fact that it's this sum multiplied by this sum. But here, right, where is this the sum being multiplied is this, includes this element, and this element, and this element. Whereas right here, the sum just includes this element. And that's just because, we're doing a different summation, so clearly it's different, but that's to explain the differences. And so this has to equal 1. Well, this trivially equals 1, right? This is an inner product of the same state as 1. So now we just have to look at these other states. And so clearly this has to equal the negative version of this, or vice versa. They must be negatives. But if we notice something, we go back to this one, this right here is exactly this. So if we have that, this and this multiplied by a constant -1 are the exact same, then we can substitute this right here into this right here. And not only can we, but we have to, because if they're equivalent and we're taking a derivative and we just say, oh, that goes to 0, well, there's a condition that we're ignoring here, that these two must be equivalent multiplied by -1. And so when we say it went to 0, that's sort of cheating what's actually going on, because in reality, there is this condition on the inner product of the perturbed theta, let us say, by delta on being 1. So then we can have, okay, if we take the partial, so now if we have our full sort of equation that we're deriving, we have this partial with respect to delta I delta j with respect to this term right here. So we have sum of this and this, and we have I and j, right? So we have partial I, and we have, I don't know why I'm writing so slanted, and we have all, we'll fix that, and we have partial I, and we have partial j. And so that's our first term, right? We're taking the derivative. And now our second term is this one right here, where we have I, j, and this time we have partial I, we have the wave function, so much to write out with a mouse. And then we have the wave function, and then we have wave function and partial j. So now if this is what we're taking our derivative with, we can see that, okay, this is going to be pretty straightforward. We have, oh, it's worth noting that this is actually a negative, right? This is a negative sign, and this is also a negative sign because this negative equals that positive. Oh, sorry, that's the exact opposite of what I meant to say. This is this example right here, right, is negative. So this is negative right here. And this right here was negative, but is now multiplied by a negative, which makes it positive. So this should be minus. So now let's just do this out. This should be trivial, right? The partial of I leaves this, the partial of j leaves that, the partial of I and j, and it's also worth noting that these summations disappear, right? Because for a given I and j, notice that the kind of inconvenient format, I guess, but these I and j's are a specific number. These I and j's are variables that are iterating over all possible enumeration. So if we're looking at a specific number, then everything in the sum disappears except one term, because everything is zero except, right? If we take a derivative of a constant, it's zero. So this everything except for these terms go to zero. That's how we get rid of the sums, just in case that wasn't clear. So now we have this components, and we should specify that this is clearly, since we took the absolute values or the itself multiplied by the conjugate, it's the real, right? This is all real numbers. So we have this I wave function partial with j wave function minus this exact term right here, which I've written so many times now. And we have j. Okay, so this is our full thing. And there's a constant sometimes that's out here. I basically just dropped my constants in this, but you can put a constant out here. I think the constant that's supposed to be out here is 4. But that's not really important. We drop a lot of constants in this, right? Because if we're caring about this from an optimization perspective, then it's just, any constant doesn't really impact things. And so even if we're caring about this from a physics perspective, right, we can set everything. We always set the variables equal to whatever we want. So this is going to be the quantum Fisher information. And this is where I'll make a few notes. First of all, this is at pure states, when everything is a pure state, this is effectively, I should say not effectively, up to a constant the same as the Fubini study metric tensor, which you'll notice has the form of -1/2 partial theta I, theta j. Oh, and this is, sorry, I should specify, this is a specific I, j index, right? Because these are i's and j's of a specific example of this fidelity. This is the perturbed theta. So this is the, I'll write approximately. So this is Fisher information. This is Fubini study metric tensor, which is effectively, I shouldn't say effect, I keep saying effectively. In this case, it is truly the real portion of the quantum geometric tensor, which you'll notice, I'll write it down here in the corner. The quantum geometric tensor has the form And this is from the original natural gradient paper, which I'll also link as always. The quantum geometric tensor has this form, which you'll notice is extremely similar to what we just wrote. This is the partial of I theta of I. This is being multiplied, by the way, down here by theta. I really should have gotten on a new page. I recognize that now. But you'll notice this term right here, these two are equivalent, right? You can see they're literally the exact same. So this Fubini study metric tensor is the exact same as the real part of the quantum geometric tensor. And so you can see the sort of equivalence is lining up in what you've seen. So now we go to, that's a long time. Now we go to the actual TFQ implementation. But first, before that, even more theory is necessary. So now that we have this Fisher information, or this Fubini study metric tensor, or the real part of the quantum geometric tensor, all of these are equivalent in these pure situations up to some constant, we can say that, okay, if we want to optimize it, this is a matrix, right? This is some, as we specified, how to get the ij component of it. This matrix, we can take the inverse, or really the pseudo inverse, because this isn't necessarily guaranteed to be an invertible matrix. And we can basically do a similar technique to Newton's optimizer, where we can do this operation. So, right, we invert the Fisher information matrix and multiply it by the gradient, exactly the same as Newton's method would invert the Hessian and multiply it by the gradient. So now the question becomes, hey, wait a second, that's a lot of math, right? This is what am I looking at? How the hell do I get this, information from a quantum circuit? There's so many partials. What am I doing here? So there's a number of ways you can do it. There's a number of approximations, especially, that are worthwhile and exist in the natural gradient paper. But we're going to be looking at the exact sort of idea. And in this case, we can calculate using the parameter shift rule. And this is maybe not the best way to do it, but this is sort of a way we can cheat and do it. Maybe an easier way is to apply the theta and then theta prime, and then measure the probability of being on the all zero state. But that might be a lot more efficient, but we're just going to be looking at the exact sort of parameter shift way to do it. In fact, maybe it's a good project if you want to play around with TensorFlow-Quantum. And this technique is taken from the estimating the gradient paper that we've discussed before. But it's maybe a good thing if you want to get more familiar with it, but to actually do this other approach where you apply the two unitaries parameterized by theta and theta prime, and then measure the probability of obtaining the all zero bit string. But for now, we can see that this is effectively the same as if we simply take this operation and measure. So if we have this information matrix in this form right here, what we can do is we can measure in the observable, where it's in this format, and we can see that if this is what we're measuring, this should be theta prime, we can see that, okay, using this format earlier where we established this whole measurement operator, if we measure using this, we can get an expression for it that's basically the same as the Hessian, because this general format of taking derivatives with respect to the measurement operator is universally true for any measurement operator. So if we assume this is what we're doing, you might say, how does that help us? What the hell is this? How are we going to work with that? We don't actually have to do that operation. We can simply use this and plug in our gradient calculations for the Hessian and get an expression that's the exact same sort of format as this Hessian calculation that we've discussed previously in the quantum gradients video. And in that quantum gradients video, we also gave the explicit format of this equation, which I will once again just copy and paste here to get this. Let's see, can I paste it? Yes. I cannot, I don't know how to move this. Here we go. So this is the equivalent format where we just plug in the parameter shift rule to actually get this. Note that this is also equivalent, right, to if we do u prime u on the 0 state and then measure the probability of getting the all 0 state. And this, what is this telling us, right? This is telling us how different are they, basically, because if this is the same, well, the same transpose, then this is going to be obviously true. But if this is radically different, right, then we're going to get a low probability. And so we can see that this is, by the way, how we measure this sort of inner product fidelity. This is a way to measure the fidelity because, right, this is telling us how different is it. And then we can differentiate this using the parameter shift rule as well. But focusing on this evaluation or formulation of it, we can see that if we go and look at the Hessian, right, we're simply applying the parameter shift rule twice. So now we just have this different formulation where we have the parameter. Let's go back here maybe, right? So we have this inner product of partials, and now we have these inner product, and these are derivatives, remember, in this case, partials that we're all adding up to get a specific element in this Fisher information matrix or Fubini study metric tensor. So if this is the expansion, right, we have 4 sample-based terms we need to evaluate each partial derivative, as is true for second-order evaluations of the parameter shift rule. Then we can begin to programmatically do this. Note that this is clearly assuming that S is pi over 2 in the parameter shift rule. All right, now that last jump was maybe not entirely clear, so if you need more clarification, I refer you to the Estimating the Gradient Physical Review paper that I'll link. I don't really want to go into more theory because I just realized that this is already 50 minutes long, and who's going to watch a 50-minute long quantum theory video? Not me. So let's get into the actual implementation. All right, getting into the code now. We have our standard imports, TensorFlow, TensorFlow-Quantum, circ, SymPy, NumPy, Matplotlib. We have this is, by the way, just a trick to, or I don't even know if this is necessary. Maybe my lack of TensorFlow knowledge is showing, but to directly minimize the output, right? Normally you have some cost function in your neural network that you're minimizing, but in this case, we're just directly minimizing the output of a model. So we just want to minimize y predicted, but that's just a way to do that automatically in like Keras's sequential modeling, but that's not that relevant. So we create, to run the comparisons between gradient descent and quantum natural gradient descent, we just create a class, and then we have 2 different optimization functions. So we have some parameters, number of qubits, number of layers, the learning rate, We create the number of parameters, we create the parameter representations, and we get our generalized empty circuit input. For the readout operators, we have two kinds. We have the sum of the outputs in the x basis and the product of the outputs in the x basis, just just to be different, I guess. There wasn't any particular reason for sum versus product. And then we create our weights, which is going to be these data parameters. So there's going to be however many number of parameters there are. There's going to be trainable. So our quantum natural gradient model is going to be a controlled parametrized quantum circuit because we're going to use this for the fidelity operation in TFQ. So we don't want just a normal model, but for now we're going to skip to the gradient descent model, which has our usual string input, the readout operators, adjoint differentiation, of course, for speed, and our circuit. We specify this loss function and atom using the specific learning rates. We set the weights to be theta. This is just a way to sort of copy this variable. And so they share the exact same initial weights, so we don't cheat and one gets lucky on the initialization. So the circuit we're using is just going to be however many layers of this. Oh, I don't know why this is commented out. Of this U3 rotation, where the U3, the arbitrary qubit rotation, is decomposed into RZ, RY, RZ, and then we have entangling C knots in a circular pattern. This is just a general sort of circuit. There's, once again, no particular reason I chose this. I guess it's pretty similar to a hardware efficient ansatz, but it's just to experiment with things. So now when we want to make this comparison, we can run gradient descent where we just fit it. It doesn't matter what we put here as a target because we're not even considering it in our loss function, right? We're just trying to minimize the output. Given this empty input, we have a single batch size because it's just one input. We do however many steps and we plot this function. So now we get into the more complex part, quantum natural gradient. So we keep track of the loss by doing the controlled parametrized circuit and just giving it the input theta and just telling it, what's the output of this. We keep track of the current circuit, which is just the original. So remember, the way the fidelity operation works is in TensorFlow-Quantum at least, is we provide it with the parametrized circuit, the parameters, the parameter values, and then the non-parametrized circuit that we're comparing the fidelity to. So although in this case, right, we're comparing two parametrized quantum circuits, we only need to provide parameters for one of them. We need to make the other one static so that we can compute the fidelity between them. So to do that, we simply we're working with this circuit, right? This this old circuit, which is the original one, and we convert it from this make circuit function. So we have this general circuit, which that's just what our circuit is, right? This isn't filled out with parameters, just has variables. And so this current circuit is what we're going to feed into the fidelity operation as our parametrized circuit. Then at each step, we just specify the Fisher information matrix as a n by n matrix. We're just printing for handiness. And then we have our old parameters, which is our current psi of theta. And to do that, we have to get the circuit. So we apply the actual parameters using Circ's param resolver and just get a circuit in which all this is doing, right, is taking our, we have these parameters up here that are symbols and replacing them with actual numerical values. And that's what's called resolving the parameters. So with that done, now we can actually go through and calculate for every element, right? We're going to go through each index of the Fisher information matrix. So there's n squared elements that we have to go through. There's 2 for loops. We have to perturb the specified unit vector by numpy over 2, sorry, numpy.pi, which is pi over 2, right? Because we specified s is pi over 2 in our parameter shift rule. And then we do this for each one, and then we get the fidelity, and then we get the fidelity for each of these operations, right? Add them together as defined by the rule right here. We add them together, and then we can multiply the whole thing by -1/8, that constant out in front right here, just to handle some casting. And then we're going to want to get the gradient. So once again, we just say watch these parameters, because this isn't your typical keras model. Get the output and get the gradient with respect to that output. Now we're going to update the parameters by saying, okay, once again, this is just to handle dimensionality. This is just to handle dimensionality, so everything multiplies correctly. All we're saying is take the learning rate, multiply it by the pseudo inverse of the Fisher information matrix and the gradient. So we're matrix multiplication there. And then append a loss and plot this loss. To get this actual each index of the Fisher information matrix, we need to get the fidelity at 4 different points, the plus, minus, minus, plus, and minus, minus cases. So in each case, right, we just perturb the original theta and use that as our parameters. So we have these perturbed parameters, the parametrized circuit, which is the exact same structure. Remember, this is the same circuit, we're just changing the parameters and computing the fidelity with respect to the original parameters, which have been bound to specific variables in this old data. We've previously worked with fidelity. You can see the quantum-assisted quantum compiling video for more information on this fidelity operation. But basically, all we're doing, right, is pretty self-explanatory, computing the fidelity for each of them, for each index, adding the fidelities up, taking the pseudo-inverse of this Fisher information matrix, and then multiplying it by the gradient. And I'm going to show some results now. Before I show these results, it's worth noting that this implementation scales very poorly, where you could trivially go many qubits and many depths with adjoint gradient descent. This gets pretty slow pretty quickly, even approaching just 10 qubits and a few depth, because this scales with the square of the parameters. It does, if we have 100 parameters, we suddenly have 10,000 operations we have to do when for gradient descent, which scales linearly or approximately linearly in the adjoint case. We only have to do 100 operations. So you can see very quickly how this can become difficult. This is not the most optimized way of doing this. Even in TensorFlow-Quantum, you could probably combine these, but it's just a way of doing it that I think most clearly conveys what's going on, right? It's very clear that, okay, we're creating this square matrix, and for each index, we're perturbing these values, getting the fidelities, combining them, and that's going to be the exact value. We're doing this pseudo-inverse just like Newton's optimizer, but with Fisher information matrix. So if we get these outputs, I open up a bunch of examples. First, I want to talk about a few things. So we can see that yes, it learns much quicker than the than the normal gradient descent. And I just want to point out a few things. Here's an example. The sum is just harder to learn for whatever reason. So you can see, once again, a clear advantage to this approach in terms of the number of iterations. If I plot this in circuit evaluations, it wouldn't be the same. However, keep in mind, this is not using the traditional approximations that quantum natural gradient descent uses. And what we're showing here is that, right, this is the number of qubits, the depth, and then the learning rate 0.01 is how these files are read. So this is product, and this is sum, is the readout operators. So this is for just a very small number of parameters. We can see that with this learning rate, the quantum natural gradient becomes extremely jagged, which indicates that it's probably too high of a learning rate. So if we decrease it by an order of magnitude, we see it instantly becomes much, much better. And so this is an important sort of consideration that I don't know if this is empirically true or a priori a statement I can say, but it seems that, the quantum Fisher information and the quantum natural gradient seems to want a lower learning rate, but that's only based on a few experiments. Here's an example of 4 qubits. Here's an example of 6 qubits, depth 2. Even with this lower learning rate here, we still see some jaggedness, but it is overall much better than gradient descent. So yeah, that's the quantum natural gradient, which just uses this Fisher information matrix. I recognize that as an extremely long discussion, very rambling, but hopefully there's some takeaways that are useful from it.